Okay, welcome to our second Laplace transform lecture. I'm going to put all 4 lectures that we need to cover this material on Brightspace. This is the second one. This will be the same lecture that'll be in class on the lecture for Monday, April 3rd. Okay, so what did we learn last time? Last time we learned the definition of the Laplace transform of a function. It's equal to the integral from 0 to infinity of e to the negative st f of t dt. And you'll notice this is a function of s. When you finish the integral and you do this improper integral, remember it's improper, so sometimes it doesn't exist. And when it does exist, it only exists for certain values of s. So when it does exist, it's a function of s. So the Laplace transform transforms a function of t to a function of s. Okay, so we computed the Laplace transform of several types of functions last time. We can make this table here. F of t, the Laplace transform of f of t, and we came up with a bunch of them. So for the function 1, we got 1 over s. And remember, that's only true when s is greater than 0. And then for the function t, we got 1 over s squared for s greater than 0. Why am I telling you for what values of s? Because remember, it doesn't converge for other values of s. This improper integral would diverge. So only for those values of s where the improper integral converges. If it doesn't converge there, it's not defined on those other values of s. Okay, what else? So this is our table, and these are the individual entries. We did t squared and t to the third and all these things. We can summarize them all into t to the n power. If we transform that, we'll always get n factorial divided by s to the n plus 1, defined when s is greater than 0. It's kind of an interesting one. All right, we did a couple more. We did e to the at, and we found that its Laplace transform is 1 over s minus a, and it's only true when s is greater than a. This is the first one. It's not always greater than 0. By the way, if a is negative, then that could be actually include more than just s greater than 0. But if a is positive, this could be something less than just the s is greater than 0. It might be s greater than 7 or something like that. All right, I didn't show all the details, but we did. By the way, let me change the letter so then you saw it last time. So we did sine. Let's do sine of b times t. There's a reason why we're going to change it to b. But b is just a constant in front of t. So whatever that b is, its Laplace transform will be b over s squared plus b squared for all s greater than 0. And then if you have cosine of b times t, the result is s over s squared plus b squared, again for s greater than 0. So again, you'll have this table given to you on exams. All right, there's a few more we could do, by the way. Let me fill in a few more. You could take the time. It would take a bunch of integration by parts, but you could actually work on a function that's something like e to the at times t to the n. So in other words, these two functions multiplied together. Well, you can't just multiply the Laplace transforms because, as we know, when you integrate the product of two functions, you can't just split up the integral across multiplication. You can do across addition, but not multiplication. So you would have to do some more integration by parts. And if you do that, you'll get this formula here, n factorial divided by s minus a to the n minus 1. Okay, so it's very similar to, you can see it's sort of a combination of these two ideas from these two. It's n factorial over, instead of just s to the n plus 1, it's s minus a to the n plus 1. So when you throw in an extra e to the at, it sort of causes a horizontal shift in your Laplace transform. And this is true when s is greater than 0 and s is greater than a. So whichever one of those two is more restrictive. A couple more. What if we had e to the at times a sine or a cosine, so times sine of bt? Now you can see why we're using a and b, different letters here, because those might have different numbers. It turns out you'll get b divided by s minus a, quantity squared, plus b squared. As you might guess, if we did e to the at times cosine of bt, we would get s minus a over s minus a quantity squared plus b squared. So you can see that multiplying a function by e to the at shifts, it causes a horizontal shift. A gets replaced with s minus a. It's kind of interesting the way that works. All right, so like I said, this will be a table you would have. By the way, these are also true for s greater than a and s greater than 0. S greater than a and s greater than 0. Both of those have to be true. All right, so, and then remember the properties of Laplace transform, right? You can take if you take the Laplace transform of k times f, that's k times the Laplace transform of f, and if you take the Laplace transform of f plus g, it's the Laplace transform of f plus the Laplace transform of g. So with those two properties in mind, in our table, we could do an example like this. Find the Laplace transform of f if f of t is this function here, 4 e to the negative 3t plus 7 t to the third minus 2 minus 6 e to the 8t. Okay, so that's the function we want to find the Laplace transform of. It shouldn't be very hard. With our table, we won't have to do a single integral. As you know, we can split this up. So Laplace transform of f, it'll be 4 times the Laplace transform of e to the negative 3t plus 7 times the Laplace transform of t cubed minus 2 times the Laplace transform of 1 and minus 6 times the Laplace transform of e to the 8t. So we can use our table for these. This will be 4, this e to the negative 3t, well, that's this formula here, where a is just negative 3. So it's 1 over s minus a negative 3. A is negative 3, so that's why I have this negative 3 in parentheses with an extra negative outside of it. We'll clean that up in a minute. Plus 7, remember the Laplace transform of t cubed, that would be times 3 factorial over s to the fourth minus 2 times the Laplace transform of 1, that's just this 1 over s. It's an s. Minus 6 times the Laplace transform of 8t would be, again, that's the same formula here again, with a equal to 8. So 1 over s minus 8. Sorry, not a, but 8. All right, and so let's work on this. This is 4 over s plus 3. Plus, remember, 3 factorial is 6, so 6 times 7, that would be 42 over s to the fourth. Minus 2 over s, and minus 6 over s minus 8. That's the function. Now, if we want to know where it's defined, remember, this first piece is defined when s is greater than negative 3, because a was negative 3 there. The second piece is true when s is greater than 0, same with this one. This last piece is true when s is greater than 8, because a was 8 in that problem. So all of these have to be true. So you have to find one condition where all of these are true. So it's like a logic problem. Well, the only one where they're all true is the most restrictive of all of them, which is s greater than 8. So you have to just say it's only true for s greater than 8. That's our final domain is s greater than 8. We can't say s is greater than 0 because, a number like 1 or 2 is greater than 0, but it wouldn't satisfy s greater than 8. And I can't allow s greater than just all of negative 3 because negative 2, negative 1, they satisfy this one, but they don't satisfy the other 3. S greater than 8, any s greater than 8 will satisfy all four of them. So that's our answer. All right, so that's kind of all the stuff we learned from the first lecture. All right, well, let's start talking about how these are useful for differential equations. So this is kind of interesting. The next thing we're going to do is we're going to actually compute the Laplace transform of the derivative of a function. Okay, so how about this? Suppose f of t is a function of t defined for t greater than 0 and for which its Laplace transform converges. Right? There are some functions whose Laplace transform will not converge. So it's a function for which its Laplace transform exists on certain interval of s. Okay, then the Laplace transform of the derivative of f of t, so f prime of t. This is kind of strange. We're actually computing the Laplace transform. Maybe I should put a note up here. This is the Laplace transform of a derivative. We're going to need to know how to do this. We're going to do Laplace transforms to solve differential equations. And that's what I'm trying to do here. The Laplace transform of the derivative of f is equal to s times the Laplace transform of f minus f of 0. Okay, so this is a formula we can use. This will enable us, this is very important because it will enable us to convert the Laplace transform of a derivative to Laplace transforms of f and an initial condition. And notice there's no derivatives left. There's no derivatives on the right side of this equation. So this will provide a potential opportunity to use Laplace transform to get rid of derivatives, which will enable us to solve some differential equations. So, all right. So, if you're wondering why is this true? Well, it comes about by let's just check it. You're not going to have to derive this, by the way, in a test or anything. You can just use this formula, but you might want to know why is it true. Well, let's try it. Laplace transform of f prime is the integral from 0 to infinity. This is just a definition, right? 0 to infinity of e to the negative st times f prime of t dt. Okay, and then remember this is an improper integral, so you're gonna do that trick where you replace the upper limit with a. Okay, now we integrate by parts. So again, we do integration by parts. We let u equal f prime of t, and dv will be e to the negative st dt. Okay, and then du, sorry, I got it backwards. Sorry, I just realized I had that backwards. All right, so just undo this. I'm going to switch the roles. I'm going to let u equal e to the negative st and dv equal to f prime dt. And then what do? Du would be, if I do du dt, I take the derivative of this. That's not hard. I get negative s, e to the negative st. And to get v, no, by the way, so du would equal negative s e to the negative st dt, right? That's the expression we need for du. I also need to compute v. I use this formula here to compute v by integrating both sides. So v, if dv equals f prime dt, then the integral of dv would equal the integral of f prime dt. Well, that would be v equals, what's the integral of f prime? It would be f. Okay, so by using integration by parts, I have that this integral here would equal u times v minus the integral of v du, which is equal to, let's see, I have u here, so e to the negative st times v, which is f, minus the integral of v du. Well, v is here, f of t, and then du is this expression here. Negative s e to the negative st dt. So let's work on this. This is, by the way, so we still have limits of integration from 0. So let me rewrite this. Let me switch to a darker color so you can see it a little better. This will be, again, this will be e to the negative st f of t minus, let's just bring this negative s out to the front, actually. It would make it a plus s times the integral of e to the negative st f of t dt. Because if I pull that negative s out, the only thing left is this e to the negative st times f of t. That's this right here. Okay, so hopefully you notice a couple things. Remember, our integral is from 0 to infinity, and then I also have to take this from 0 to infinity also. Well, hopefully you notice this part right here is just equal to the Laplace transform of f. By definition, this is L of f. Just by definition. That's how we defined Laplace transform of f. Okay, and then we just have an s in front of it. So, and then what about the rest of this? Well, when t goes to infinity, this e to the negative st goes to 0. Okay, and then when I plug in 0 for t, right, so this becomes essentially e to the negative infinity f of essentially infinity, which this whole thing equals 0. And then minus e to the 0 f of 0, right? Because I'm plugging in 0 at the bottom for t. So altogether I get negative f of 0 plus s times the Laplace transform of f. That is the Laplace transform of f prime. Just proved it to you. That was the formula I gave you a minute ago in a different order. Right? That's the same thing as this here. That's very important. In fact, before we do an example with this, let's put it in our table. So let me scroll over here. Every time, scroll up, excuse me. So there's not much room left in our table, but let's add it in there anyway. Put it at the bottom here. I guess, yeah, how about this? I've got technology here. I can bring this down, move this down. These are just some properties that we don't really need to have in there. Okay, that's good. Now, let me extend this down, make a row in our table. The Laplace transform of f prime of t, right? F prime of t is, that's what we just figured out. It's s times the Laplace transform of f without the prime minus f of 0. Okay, so notice something, by the way. You can't find the Laplace transform of a function, of a derivative of a function, without having this initial condition. It's the value of f at 0, at 0, at t equals 0. That's an initial condition. So it turns out because of that, we only use Laplace transforms to solve differential equations when we have initial value problems, initial conditions. So it requires an initial condition. It requires the value. Okay, well, nevertheless, now that we've seen the Laplace transform of a derivative of a function, let's do an example on a differential equation. So scroll way down here. Here's an example. let's start with a simple differential equation, something we probably saw back, the first couple weeks of this class. So consider this differential equation. How about 7y prime equals 3y plus t squared minus 4 e to the 6t. Okay, this is a perfectly valid differential equation. You might remember, I think this one is not separable, but it is linear, so you could actually solve it using an integrating factor. You might have to remember that. You might have to review that before the final. Okay, so I'm just saying consider it, though. I'm not saying solve it. Let's. How about this? Here's a new technique that we haven't seen before. Now that we have Laplace transforms at our disposal, apply Laplace transform to both sides of this equation. Remember, you're allowed to do, you have an equation, so you're allowed to do the same thing to both sides. Even though it's a differential equation, you can still do that, right? So that means, what do we get? Let's try it. We take the Laplace transform of 7y prime equals the Laplace transform of 3y plus t squared minus 4e to the 6t. By the way, y is some function of t here, right? So when I write y, it's really some y of t. Okay, so, well, we can use our properties, right? So what can we do here? I hope you're thinking we can definitely take that 7 out. So we get 7 Laplace transform of y prime equals 3 Laplace transform of y plus the Laplace transform of t squared minus 4 times the Laplace transform of e to the 6t. Okay, well, what can we do? Well, the left side, we can just use that formula, right? Isn't it 7 times? And we just did this. We just learned the Laplace transform of the derivative of a function is going to be s times the Laplace transform of y minus y of 0. Right? That's what we figured out. That was the last row we just put in our table. Right? I mean, if I scroll out, that's the formula we just came up with right here. We were using f prime instead of y prime, but that means the Laplace transform of y prime is s Laplace transform of y minus y of 0. It's the same thing, right? That's the same thing. Okay, so let's scroll back in. Okay, on the right-hand side, well, this is just the Laplace transform of y. We don't know what y is, so we can't figure that out yet. So this is be 3L of y plus, although we can figure out this one. This is the Laplace transform of t squared. Hope we remember this. This is n factorial, so 2 factorial over s to the 2 plus 1, which is 3. And then the last term, minus 4. Laplace transform of e to the 6t, hopefully remember that one. That's 1 over s minus 6. Okay, so let's do some work here. This is, so I don't know, we can distribute this 7, so we get 7s Laplace transform of y minus 7 y of 0. Right, that 7 got distributed. Equals 3 Laplace transform of y plus 2 factorial is just 2. 2 over s squared minus 4 over s minus 6. You might wonder, well, what do we do with that? Why did we do it? Here's the idea. So next, now, solve this expression for Laplace transform of y. You see how it's Laplace transform of y is occurring in 2 different places? This is very similar, by the way, in case this doesn't look like something you would know how to do. What if I gave you this equation here? Just forget about this problem for a second. Suppose we had this problem here. Suppose we had 8xy minus 23 equals 4x plus 2y. And I said solve for y. Well, there's two steps. First of all, you have to get all the y's together. Get all y's on one side. So you see how there's a y term here and there's a y term here. I'd have to get them all on one side and all the other terms on the other side. So I'd subtract the 2y and I'd get 8xy minus 2y. And I'd add the 23, so equals 4x plus 23. So just going to rearrange some terms here. Then I want to get y by itself. In other words, my goal is to end up with y equals something. I have y in two different terms here, so I factor it out. And I write this as y times 8x minus 2 equals 4x plus 23, and then we've got it, right? We can just divide both sides by 8x minus 2. And so we get y is equal to 4x plus 23 over 8x minus 2. And you can't cancel anything there because of all the pluses and minuses. So that's the technique we're using. We're going to use that technique over here to solve for Laplace transform of y, to get that by itself. So we bring this term to the other side and bring this term to the right side. So we're going to get 7s Laplace transform of y minus 3 Laplace transform of y, because I had to subtract this over, equals 2 over s squared minus 4 over s minus 6 plus 7 times y of 0. We're almost there. I've got Laplace transform of y in two different places on the left side. Factor it out. 7s minus 3 equals 2 over s squared minus 4 over s minus 6 plus 7y of 0. And by the way, if this were an initial value problem, I didn't write it down, but suppose it were an initial value problem, then when I gave you the differential equation, let me scroll out a little bit, when I gave you this differential equation back here originally, I should have also told you y prime of 0 equals something. Something like, let's say y prime of 0 equals 2. So let's pretend that was part of the original problem. This is just an example. So if that's also given to you, then at this point, scroll back to where we were, I could replace with what I could replace, sorry, I didn't mean to, that was a mistake. When you have a first order differential equation like this, when they give you an initial condition, they don't give you y prime, they just give you y. I meant to write y of 0 equals 2, not y prime of 0. So sorry about that. Okay, you only need one initial condition when you have a first order differential equation. We'll do a second order later. And you'll need a y of 0 and a y prime of 0. Okay, so we know y of 0 is 2. Let's scroll back to where we were. We're here. Well, that means we can just replace this with 2. So this whole thing would be 7 times 2, which is 14. And we're almost there, right? So Laplace transform of y, I just have to divide both sides by 7s. Sorry, I made another mistake. That's not 7s minus s, it's 7s minus 3, right? Because that's 3 there. I have to divide both sides by 7s minus 3. So this all gets divided by 7s minus 3. And if you split that up into individual fractions, you'll get 2 over s squared times 7s minus 3 minus 4 over s minus 6 times 7s minus 3. Sorry, I didn't write that very well. 7s minus 3. Right? I'm just essentially, instead of dividing the whole thing by 7s minus 3, I'm multiplying this whole side by 1 over 7s minus 3, and then I'm distributing it. So it becomes in the denominator there, it becomes in the denominator there, and it'll go in the denominator here. So it'll be plus 14 over 7s minus 3. So look at this. All we've done is we started with a differential equation, took the Laplace transform of both sides, and used all of our properties. We didn't even have to do any integrals. We just used the Laplace transform from the table and its properties. and we've got this. This is important. We don't know what the function y is, y of t is, yet. But we do know its Laplace transform. I guess I should capitalize Laplace. We do know its Laplace transform. Our goal to solve the differential equation would be to find the function y of t. That would be our solution. And this is an alternative way to do it, because if we can learn how to undo or reverse, so if we can do a Laplace transform in reverse, we can get y of t. Okay. And that's the next skill we need to learn. We need to learn how to take the Laplace transform in reverse. Okay, so some good news on that. So let me zoom in on here. This isn't written very well. It should have been. It should say s squared, right? This is s squared. Let me erase it and make it look better. It should say s squared. This is an s. I'm avoiding using 5s right now because I want to make sure all of these look like, aren't confused with 5s. So some professors will, maybe I'll start doing this. They'll put a different font on the s to make it look like an s. And I think I made that same mistake here. I apologize. This should have been a 3. Wasn't very careful. That is 7s minus 3. They're all 7s minus 3, right? Now, if we can do the inverse or the reverse of the Laplace transform on all of this, then we'll have our function y. As you can imagine, since Laplace transforms split up over addition and subtraction, so do inverse Laplace transforms. So really, I just need to find the Laplace transform of this, and then the Laplace transform of this, and subtract them, and then the Laplace transform of this, and then add it on to the other two. Okay. In fact, we could probably already take the Laplace transform of this one right here, the inverse Laplace transform, because what you could do is you could look up in the table to see what that one looks like. These others are not so easy because you won't find these in the table. All the things in the table have if you look in the table again, you'll see most of them have linear terms in the denominator. Sometimes they'll have square terms, but not just generic polynomials. If I were to FOIL this out, it would just be a big polynomial. Same thing here. So it turns out the technique we need to do, if we wanted to take the inverse Laplace transform of all this, we'd have to use a technique called partial fractions. Okay, so what do I'll show you what that means, but it's just a technique to write each of these terms in a slightly nicer form that we can find things that are in our table to undo them. Okay, so that's the next technique we have to look at.